Swayam Prabha. Digital India. Educated India.
So just to repeat a few things. So we ultimately want to do the connected bodies, but before that you should master how to look at the various kinematic equations of single body, and then how to handle it in different ways. So it's a vectorial equation. So everywhere we have to have that vectorial sense. So if you want to write it in the form of arrows like this one, so VB is known to be moving vertical, VA is horizontal, and then this is the velocity of B with respect to A. We know that it is perpendicular to AB, and if this is theta, so this is also theta, so we can represent it in this manner, right? So here again, we do not know that it is moving up or down, okay? Only that we know that it is perpendicular to this. So this you can write it in the form of your ij, and so this is say you can write it as cos theta I, okay, assuming that it is this way. And so here you can see that I have eliminated one step here. Otherwise this I should be writing it as omega k cross L cos theta I and plus L sin theta j, which would have come anyway in this manner. So this is, if you can put this step, obviously if you once you get used to this kind of things, so you can put this step fast, okay, right away by examining this one. So you can put it like this one, or so using this we can using j, and this is what we have done, VA plus, this is in terms of your vector algebra, this is what we have done. This is, and then you can solve for, this is ith equation, and this is in the j cap equation, and then this is solved for omega and given VA, okay? So that's understandable. This is what we have done, and this is in terms of ij, or you can also write this relationship in a semi-graphical manner. This is vector algebra approach. Directly, and if you go for semi-graphical, this is faster and intuitive as well. So you have this is a velocity diagram. Okay, in the velocity diagram, so we represent, we have an xy axis, there's an origin here, and then this is VA, so this is O and A. OA represents velocity of A given to us, and then after that you have to add L omega and at an angle of theta. So that means that you have to draw a line here at an angle of theta here.
Yes, sir.
Just a minute. Yeah. Yeah. Any question, please? Yeah. You have any question? Somebody is trying to say something.
Isn't it sin theta and minus cos theta in omega?
Okay. Yeah. You're right. In fact, that also turns to be that one. Yeah. Thanks. Should have been more careful. And similarly here. Okay, thanks very much. Yeah. Okay, so this is the velocity diagram. This is a semi-graphical approach, which I was telling. In the sense that we draw the velocity diagram, and then from that, using the trigonometric relations, we straight away write down some equations here for unknowns maybe. So what we have here, this is theta, and then this is what L omega, either up or down. So this is velocity B with. So last time also I was told you this as much. So the idea here is that finally when you add these two, you're supposed to get a VB on a vertical direction. So there's no point in going in this direction because you are never going to have a vector from origin in a vertical direction. So this is VB, right? So this is whatever you have written here, we directly wrote it in a diagrammatic manner, or you could have gone it in blindly in a vector algebra, IJ components, is equally good enough. And this is a gives you an intuitive idea how the velocities are related. So from here, instead of writing down this and solving for that, so we can directly write it here. So for example, VB here, if you want to, is nothing but BA by tan theta. And so L omega here, we can even write it's nothing but BA by. So this is, I'm emphasizing in some way we have done it last time itself, but then I'm doing that in a recapitulating so that the things will be really implanted in you thoroughly. Okay, so this is, so what all we have done here is done in just 2 steps by just examining the velocity diagram. Okay, and then we can also do the acceleration analysis. There's also another approach here, which probably I will tell you, just let me finish the acceleration diagram. So the acceleration analysis here, so honestly, I prefer this one, though, or my experience says that the students tend to use this one because they can blindly follow some IJK and so on. So that's easier. But this would give you much more intuition to the problem. So the acceleration analysis, so if you want to get the acceleration, acceleration of B here is acceleration of A and B with A, the normal component, and so together they will become acceleration of B with respect to A because this is circular motion. So you end up having 2 components. So here again, now if you want to just go by ABA, so ABA is what? You know that it's minus omega square B with A, and this is alpha K cross or BA, right? So this is how we write, and then so ABJ and AI, and this is minus omega square. What is that? L cos theta I J And here,
Sir,
ah,
a part of the right side is being cut out, sir, from the screen.
okay, yeah, I know. Yeah, keep reminding me. Yes. Yeah, so what I was telling is that this equation, you know, how B is related to A, and there's a circular motion, two components, otherwise it constitutes acceleration of B with A, which will have a normal and a tangential component. So the normal component is minus omega square RBA, and the tangential component can be written as alpha K cap cross RBA. And so this is RBA is like this, and K cross. So for that, we have L K cross I, whatever you have here is L cos theta J, and this is L sin theta I cap. Okay. So this is how you can write the relationship between acceleration. So you can write down equation for I, which is AA minus alpha L sin theta. And so similarly for J, we have AB is minus omega square L minus alpha L. So you have two equations like this, and you can solve for, usually AA is given to you. Okay, you are supposed to solve for alpha and AB. So these two you can solve. Every other thing is known. Theta is given to you, AA is given to you, omega is obtained from the previous velocity analysis, and then you can do this. Okay, this is this one. I'll still go further. I continue here. Okay, so this is semi-graphical analysis. So this requires some part of your understanding, right? When you do it, I think if it is slightly inclined, I'll go back to this. Yeah, so going for semi-graphical method. So just it's more or less on the lines of velocity analysis. So here quickly, so we have X and Y axis here, and this is the origin, and anything measured from origin gives you the acceleration here as well as the direction. So here we know the acceleration of A this is acceleration of A, let us say, call it A here, and then so to that we have to add the normal acceleration. So the normal acceleration here of B with respect to A goes from B to A at an angle of like this one. This is an angle of, sorry, this is not theta. This is just along the line here, and this is theta here. Okay, so this is, and we know that its magnitude is L omega square. It's an angle of theta, and to that, if you add the tangential component, so obviously the tangential component is in the tangent to the circular motion. So that means that it is in this direction, and that will be, so if this is theta, we know that this also will be theta, and so this is theta here. And to this, so if this is what you're going to add, and what more we know is that adding these two, so let's say this is B prime, and you get B, okay? So AB will represent the acceleration of B with respect to A. And adding that acceleration of ABA, so you are supposed to get an acceleration of B in the vertical direction. Okay, so this is the acceleration diagram. Okay, this is the coordinates x and y, and you go on writing in this manner. Okay, so that means that so since this is downward here, the acceleration of B is going to go down in this direction, okay, of a certain magnitude. So here also you can make the equations for horizontal component and vertical components. A quick one, the horizontal component or even the vertical component, for example. No, I think we should write horizontal component. Why? So if you have right AA, so by looking at this one, so we have L omega square cos theta, and what is this one? This is alpha L alpha sin theta. Okay, so similarly you have, so you can make these equations by looking at this one. So you don't really have to solve all these things. Here, for example, if you want to get from this equation, you can directly get, what is it? You can directly get alpha. And similarly, you can make the equation for AB. So AB is nothing but L omega square sin theta minus alpha L cos theta. So that's what you put here, and then you can solve. So you can see very clearly that these semi-graphical approaches are more intuitive and much faster, much faster. But sometimes we'll stick to this IJ when, for two reasons. When this becomes too big, sometimes it may not be possible to really make this graphical approach. Okay, but be conversant with both the methods. So that means that you should know how to make this, split it into IJ and solve. That's number one. Number two is that make so this equation, for I forgot that here, so you can write this one. This is in the form of so this is this equation in the form of arrows, and so that can be translated into this one, that can be seen in this manner, and so you have three methods. You have really three methods by which you can finally determine all these accelerations and velocities and accelerations. Fine. So quickly, I think towards I repeated this one because just to show that there are three methods by which you can solve these problems, and then you should be conversant with all the three methods. So tomorrow when there is a tutorial, so you will be asked to solve by all the three methods. Some problems will be there and you will be asked to solve by all the three approaches. So the other interesting, looks very simple, and is the rolling of a disk on the ground. We have solved for velocity so there's a disk here which is rolling on the ground, and the center has a velocity v. So let us say, and then you would like to have analyze the velocities and accelerations of various points. Okay, so one of the things that usually is given, for example, for point A here, and so disk one of the constraint is that disk rolls without slip. Without slip means that, for example, if you have 2 points here, A and A prime, and A prime is on the ground and A is on the wheel. So if there is no slip means that the velocity of A and velocity of A prime are same. Okay, in fact, this is more general definition, because tomorrow you are going to see some bodies which are moving with in an absolute sense, but sometimes we say that there is no slip, which means that they have the same velocity and accelerations. And so here, so if there's, so that means that the velocity of A and velocity of A prime are same, okay, in the horizontal direction. Because the A, though obviously you can see that it is tangential, but sometimes A after a little instant, it also starts having velocity upward. So only at this instant, so the velocity of A and A prime are same, and essentially they are zero. Okay, so this is the constraint. The constraint of motion is this. Because of this, VA is VA prime. And using this, your velocity relationship, VC plus A. So this last time I put it. And so if you want, so we can put it as so A with C. So you can very clearly see, if you want, you can put it as maybe here. So this is the relationship, your algebra equation. So from this, we can very clearly see that here, A with C is RJ plus I and BC. So another thing is that omega here, if you have assumed like that, so we can even, this relationship is for omega K is assumed to be, there omega is assumed to be counterclockwise. So if you know it, then you can use it. Otherwise, to be more precise, since you are assuming a clockwise, so you have to use a minus omega here, and which says that minus minus and plus, and so anyway, so this is looks a little trivial, but this is how precisely you can do that. So similarly, this is about point A. What about some point B here? If you have a point B here, what is the velocity of B? So is the velocity of B downward, or is the velocity of B horizontal to the right? Okay, it is actually, it's a combination of these two. So velocity of B, you can say that velocity of C plus B with C. So without going into too much, and what I'll straight away write. So the velocity of B, I can straight away write VC is V. So if you want, we'll put it as V naught and A naught, just for the sake of no confusion. So we say V naught, and this is, what is it? This is horizontal, and B with C. So B is rotating about C. So if you assume that C is stationary, the motion of B is circular and going down using this omega. So this is nothing but, how much is that? R omega downward. Right? So this part is R omega downward, whereas the VC is V naught. So that means that it is really in a If you want, we can write it as V naught I minus R omega J. If you want, you can write it. Or in a vectorial fashion, this is V naught and this is R omega, and again that's equal to V naught. So the combination of these two is like this. So this is B. So the velocity of B here is actually like this. It is at an angle of 45 degrees. You can see these two are equal. So this is going to be a 45 degree. So like this, you can find out velocity of C, velocity of D here, and velocity of E here. So how is the velocity of E? So you can very well see that velocity of E is velocity of C, E with C, and this is V naught. And this you can see that it's nothing but R omega again in the horizontal direction. So this is again V naught, so it's nothing but 2V naught. So it is having a magnitude of 2V naught and it is in the horizontal direction. So that means that the top point here will be moving at twice the speed of the center of the disk. So if this is V naught, so this is twice the V naught, and whereas V is at an angle of what is the magnitude? You can very well see that this magnitude is nothing but √2 V naught. Okay, it's √2 V naught. This is, how is this? So this is √2 V naught. Maybe I'll just draw it here. So this velocity is 45 degrees. So this is various points are going to have this velocity. In fact, you can find out the velocity of any other. This is very interesting. We are going to talk about something like instantaneous centers later. So here, this point is having a zero velocity. So what does that mean? If it is a zero velocity, means it is, it seems to be a center of rotation as far as the velocity is concerned. So everything seems to be rotating about A, and you can see that. So if it is rotating at an velocity of omega, angular velocity, so it will be going like this. So it is going like this, and it's going like this. So we will talk about the instantaneous center a little later, but you can find out the direction and magnitudes using this as a center of rotation. Okay, so this is this velocities. Now let's look at quickly the accelerations. So if the acceleration of this one is a naught, then we can find out the acceleration of everything else. For example, we can find out acceleration of A is C with A. I'll straight away write a normal, and C with A tangential. So here this is given as A naught, and C with A. So now that you are quite conversant, I'm sorry, A with C. So this is. So A with C, the normal component is, how is that? It's A is rotating about C with an angular velocity of, so it is R omega square, and it is directed from A to C. And then what about this A with C? So that is the tangential component, and A is rotating about C, and then it's given as alpha is the angular acceleration, so that means that it is going this way. And let us just see, so it is R alpha, and it is in the horizontal direction. Okay, so you can you are quite conversant with now how I'm putting these arrows. So that means that you have A naught minus R alpha plus R omega square, the upward direction. So this is the acceleration of A. So interestingly, so what is that you have here? So you have this A naught minus R alpha, and this is R omega square. This is the acceleration of A. Okay, so this is how you can put it. In fact, since many things are coinciding here, so we can even write many of these components separately. Okay, how is that? So that means that interestingly, so this point A is having an acceleration like this one, right? So that means that the velocity of A is 0, but the acceleration of A is not 0. Okay, it has certain components, both horizontal and vertical components. Okay, so like this, so we can find out the acceleration of B. So acceleration of B, if you want acceleration of B, for example, so it's acceleration of C plus B with C and B with C tangential. So I'll just straight away draw this acceleration diagram. So acceleration of C is what? So it is having like this one. So this is acceleration of C, and the normal component of B with C is, how is that? Let me draw them bigger. So this is acceleration of C, and B with C, the normal component, will be actually tracing back from here. I'll just write down here. So this is so you came up here, then come back, then what else? Then what else is that there's an alpha here. So alpha is okay. In fact, there is also one thing which I just missed, is how to find if A naught is given and how to find alpha. How do you find alpha? This is a very important aspect which I assume you would be able to get it, but how do you do that? So what is the constraint you are going to put here? So for that what you need is that, again, we go for the constraint here. The point A here, point A, the constraint as far as acceleration is concerned, as far as A and A prime are concerned, so the velocity of A is the horizontal component of A is 0. What can you say about acceleration? Okay, so the point A is also similarly is not going to have any acceleration tangential to that. Okay, so that means that velocity of A, I'm sorry, acceleration of A, the horizontal component, is 0. So the horizontal component of A is 0. Okay, so using this, so we can, will you try this one? Using this, so just making this acceleration of A relationship, then we can say that the alpha is here A naught by R. So I'll leave this as a little bit of exercise. So this is, so you can find out the acceleration of various points using this relationships for various points. Okay. Now let me just introduce one small thing which, so can you find out the various acceleration of various points? Okay. So I'll just introduce you one connected body, that is crank and connecting rod mechanism. So this we use this example, we'll take it up often. And this has, as I said, it has a crank here. Yeah, this is a very important example, and which we keep taking it again and again in many situations. So here, this is a crank, just take 2-3 minutes, crank and a connecting rod. So if this is given theta, you can find out phi. Okay, with that you can find out phi as from the relationship trigonometry. So r sine theta is equal to L sine phi, and you can find out, sorry, you can find out phi as sine inverse okay, so that's as far as what happened, signed out. Yeah, what is this? Gender? It was signed out? Who is that? Somebody else is using, so you cannot use ours before 10 o'clock. Cross. No. Can I continue? Hello, can you hear me?
Yes, sir.
Yes, sir. Oh, okay. Okay, because there's something saying that it's signed out and all that. So we are just trying to give you a very important example here. So this is a crank and connecting rod like this. So we have to do the velocity and acceleration analysis. So I'll just introduce you. So these are connected bodies. So a crank and a connecting rod. So we can apply our one rigid body equation for AB and another rigid body equation for BC. For example, if this is omega 1 and this is another different angular velocity, and this is one angular velocity and one acceleration. So each body has a particular angular velocity and acceleration, okay, related to that. And if you have another body, they can be completely different, but however, they have to satisfy the constraints. So what are the constraints? The point A is fixed here, and while C is moving on a horizontal guide. Okay, so this is the relationship. So how do we make, so VB we can find out very easily. I'll just put down a quick equation. So it is nothing but, so it's a rotation. So this will elaborate tomorrow, and then we can get velocity of C with respect to B again here. And we can relate all these things to one equation. And we can solve. What are the unknowns here? Give, for example, velocity. Omega 1 is given. Can we find out omega 2 and VC? So we should be able to find, solve this vector equation for two unknowns. So I'll stop here and we'll continue this and we'll do something more. So I'll send the tutorial problem sometime before lunch. Okay, thank you.